In a recent video where I adapted a disco projector to do a simple pattern, it was to emulate stained glass light with the light shining through it. I kind of skipped a bit in the video where I made the circuit board, and it was to keep the video smaller in size, but a few of you wanted really to see what was involved making the circuit board, so here is the making of the circuit board, and I have tweaked it, I've adjusted it. I've added a discharge resistor across this capacitor here, and I've also nudged things. I've added a crop line here because it turns out the circuit board doesn't have to be so big, so that bit, the big clive.com bit in reverse, that there can be cropped off to make the circuit board smaller if you want to make it fit into a piece of material you have. And it's also got a couple of arrows to show which way down goes down. It's worth mentioning that pattern this projects is inverted, so the LEDs at the bottom will actually be at the top of the image when they go through the lens. But anyway, the making of the circuit board. To design this, I use Sprint Layout 50, I think it's Sprint Layout 60 now. And I chose that piece of software because it's the closest to what I used to use. Boardmaker 1 is what I started making printed circuit boards with. It was an old DOS package, which was really very down-to-earth and simple, and that's what I like. If I was designing a really complex package, then it'd be quite useful to have it correlating the printed circuit board design to the schematic. But in this case, it's much easier just to bang down tracks and pads. And that's what I did here. So basically, I drew one LED. I could have imported it from the library. I just drew an LED using the outline and the pads, and then I just copied it, because you can do that. You can highlight the area you want, copy it, and then just clone it. And I cloned a row, cloned that row down, put all the tracks in for one section, and then cloned it repeatedly down to actually fill up the whole space. It was just the easiest way to do it. Because I wasn't sure about the capacitor I was going to end up using, I allowed a footprint that can accommodate a wide range of capacitor sizes here. I played safe with the full mains voltage across this. This was originally designed for UK voltage. It'll work in America as well, with different capacitor value here. I put a couple of resistors in series for the discharge resistor cross capacitor, but only one is needed here because the voltage across the LEDs is much lower. It's less than 200 volts. So, to make the actual circuit board, I converted this into a transparency, and the transparency is printed onto a special translucent film. It's not like standard inkjet overhead projector type film. This is specifically aimed at the silkscreen industry because it's for making transparencies, and the main thing is it absorbs a lot of ink. The one side is smooth, the other side is physically squeaky. It makes quite a strong squeaking noise, and what I did was I printed off the first image onto an A4 sheet of paper, noted with a pen, just put a wee arrow at the bottom which way it came out the printer. And then I got a piece of this material and taped it across that area with the ink receptive side up, and then fed the same sheet of paper through the printer. And the reason for that is that this film is fairly expensive, so it helps when you don't waste whole sheets, you just use a small section. So you also set the printer settings to absolutely pile the ink out. Maybe glossy photo is going to be enough, but in my case, I chose glossy photo plus. I went to the color adjustment settings in the Epson printer and the control interface from the laptop, and I set all the color settings to their most extreme levels, so it produces a fairly dense black. There's a very strong contrast. Otherwise, it sometimes tries to make a black using cyan, magenta and yellow, and it's not quite the same, but this does soak in a lot of ink, so it's not that bad. So I've got the transparency. All I need is the circuit board material. You start off, I used to buy the light sensitive pre-sensitized material, but I've switched to using the dry film stuff off eBay because it's easier, and it means when you screw up you can strip it all off and start again. You can't do that if you buy the pre-coated boards. So I've taken this piece of standard fiberglass laminate with the copper on one side, and I've cleaned it using a standard sponge pad. I'm just going to grab that. A standard scrubby pad with the sort of nylon scrubby side, which is great for cleaning the copper. This is useful during the whole process. You can use the other side for parts of the developing process as well. These are quite useful in the workshop. So now I've got the film and I'm going to apply it. So the film, as it's supplied, I'm going to keep this out of the light too much. So this is a sort of bluish coloured film, and it's actually a layer of sort of gel sandwiched in between two layers of plastic. So to start off with, you have to expose one side. You have to remove one of the clear films. So if you get a bit of tape, sticky tape, and you just stick it on one side, and then you get another bit of sticky tape, and you stick it on the other side of that corner, and then without letting them touch together, you peel them apart. One side's got to give, and in this case, it's this one's given. So this is a clear coating that I'm removing. I shall also remove that tape, because otherwise it sticks everywhere. Now I'm going to place this. I'm leaving the clear coating on the other side to protect it, and I'm going to mist the circuit board with water. I just find this the best way to do it. The videos online show people putting it through laminators. I've never had any luck with that. So I'm going to lay this down, and when it sticks on, it will be like putting a cover on a panel on a mobile phone. It's the protective screen film. Very similar. You want to sort of like squish out any sort of water that gets trapped. And the way I do that is with this from eBay. It's for vinyl, and it's basically a squeegee for vinyl with a felt edge, and you just spread it out like that to make sure all the water is pushed out from underneath the film and there's no little pockets of moisture trapped. I shall just smear that off with my hand. I've just swept water across the top of it. It doesn't really matter that much. And previously I've used a hairdryer to put this, to actually cure this, because you want to actually heat it to actually put it on. I should be watching my time here because I don't want to expose this to the LED lights too much. This time I'm using an iron, a standard domestic iron. There's not many uses for these other than this, because I certainly don't use it in my clothing. So use it to firmly iron that material on. And what that'll do is it'll kind of fuse the material onto the circuit board. Now this is where I wonder if I should actually be using a sort of like coupler layer, like a piece of paper or something between it to couple the heat on, and also kind of like pack in for any slight irregularities in the surface. But I've got this at a fairly low setting. I've got it at setting, it's not even at setting number 1. I'm not sure what that is. I use this for preheating circuit boards as well. But that looks pretty good. Now I'm going to look across that. It looks actually pretty good indeed. And that's it, got the light sensitive coating on it now. So the next thing I'm going to do is I'm going to expose it using ultraviolet. You can also use daylight. It produces quite a vivid change. I'm going to let this cool down first, and then I'm going to put this transparency on, and I'm going to expose it using ultraviolet light. So I'll be back in a moment. So it's now been exposed, and one good thing about this material is when you expose it, it physically changes colour. This is good because it means that you don't have to use an ultraviolet light source to do it. You can use just daylight or a standard compact fluorescent lamp or an LED lamp. It will just take a varying length of time. So now we have to expose the material now and take the other layer of plastic off. So I'm just going to put a bit of tape in there, peel it up, and now that other protective film is coming off. Let's get that off my gloves. It's going to stick everywhere. And now we need to make our special developer solution, special secret developer, which is a bowl with 8 grams of sodium carbonate in it. Now, I went online to find sodium carbonate. The Isle of Man's not great for chemicals. I went online and bought sodium carbonate from various scientific sources, and it was quite expensive. And then when I was in the local supermarket, I saw these soda crystals and thought, oh, let's see what chemical that is in case it's useful. And it was sodium carbonate decahydrate. Now, note you can't use bicarbonate of soda. It has to be used sodium carbonate. So soda crystals, that's what I use. And that bag will last a very long time, because this is just 8 grams of those crystals, and I'm going to make it up with 500 millilitres of warm water. You can reuse this a few times. You're making lots of circuit boards, but it will gradually reduce in effectiveness. So I'm actually going to stir that with the circuit board itself. And what's going to happen now is where the material has been exposed to ultraviolet, it's hardened, it's cured it. But where it's not been exposed, it's still soft, and it's going to gradually eat off. And you can possibly see it kind of getting paler and clouding a bit. And this is where this is quite an unusual material, because you do have to help it on its way with these type of materials. Whereas the traditional circuit board developing materials, it would just wash off in really nasty solutions of like caustic soda and stuff like that. This stuff kind of softens, but it helps if you either rub it with your fingers, take it out every so often and rub it. I'm looking at a little line I've got there. I wonder what caused that. That can be tweaked afterwards, or you can use the sponge. And the sponge is quite good because it kind of gets into all the nooks and crannies and it helps remove that material. It just needs that help off once you've softened it. So let's keep soaking that until it looks like it's all gone and I've got a nice clean pattern. And importantly for me, in the production of this, I do want the central indents in the tracks to wash out. I want that hole in the middle of the copper once it's etched, because that will help guide the drill. So this is looking pretty good. It's quite time consuming. Well, I say it's quite time consuming. It feels like when you're doing it because it is a time critical thing, but it's not that bad. Still annoyed about that little flake there that's not going anywhere. It might be that when I expose that, it's possible that something landed in the circuit board. I'm going to have to check the exposure unit and see if it's got dust in it. So I'll keep going, and even when you think you're done, it's worth going a bit longer. You've got a good, generous exposure time. It depends the contrast of material. It's important when you're exposing this that the transparency is actually sandwiched right down hard onto the copper, because if it isn't, you'll get a fuzzy outline and it's not as good. So this is starting to look pretty good. I found it quite awkward when I started doing this because I'm really not used to rubbing it like this. I would have thought in previous circuit board development techniques, particularly my really just repeatedly failed attempts at the printed circuit board making with toner, laser printer toner, that was just terrible for the when you were trying to clean the circuit board and you tried to clean off the paper residue and leave the toner on the circuit board, you'd quite often chunks of the toner would leave as well. I never had any success with that. It was just, it didn't work for me. This works fine. Although with any of these systems, it takes a bit of getting used to. You have to experiment with it a lot. So I'm going to keep developing this. I'll just keep going because it just gives you an idea of what's actually involved, the time involved, and what can go wrong. Still not getting the bits out between the tracks here, and if you don't do it for long enough, you find that, you know, the bits between the pads won't come out, the fine details, and it will just end up making everything look a bit fuzzy. Technically speaking, I suppose it's not helping that I'm doing this under the bright studio lighting, because it will be trying to harden it against the developer. But it's getting there. I'm getting fairly clean indents in the middle of the pads, and that's really what I want here. When you first experiment with this, I'd recommend not going straight into your first circuit board. Get little snippets of material and experiment with exposure times and different sort of lights. Get a bit of glass to press down on the artwork to make sure it mates to the copper properly. I use an actual ultraviolet exposure unit, which has a foam pad in it that presses things together. And quite nicely, it's got the tubes in the lid of the unit, so you can line all the artwork up and then lower the lid down, and it accurately locks it all in place. So I'm going to give this a bit longer because the bit I'm concerned about here is between the pads isn't actually clearing. If it takes too long, I'll just pause. It is looking better though. Let's get the sponge into it. That can get into the nooks and crannies better. At the end, it even helps just to soak the sponge and rub it. Now, didn't Sino, they did a system whereby you just actually had sponges with the chemicals loaded and you used them like this, where you didn't actually dip it in liquid at all. It was purely done with a sponge. not just for putting on the ultraviolet photoresist in the first place, but also for developing it, possibly even etching it as well. This is looking a lot better now. I just want to make sure that I've got all the little bridges out between those pads, and the time varies, you know. If I could do another circuit board with slightly different exposure and development times, and it would, you know, this would just be flying off, or it could take ages. I could only be halfway off. It depends. It depends on the concentration and temperature of the developer and sort of exposure time and the material itself. So there's a lot of variables, but you get used to it very quickly, and then it becomes second nature when you're making the circuit boards. Okay, this is looking pretty good. I'll just give it a tiny bit more. See, I always do that, don't I? I say, oh yeah, almost there, finished, and then I don't. You do have the option of skipping forward. That's one of the best things about YouTube, isn't it? If a video drags at all, you can just skip. So that is pretty much it. If I do get any bridges between the pads, I will simply just take them out when I'm drilling. I'll just touch the drill in that area and it will just remove those little links. It's happening just in one area in this. It's happening just at this end here. I'm not sure where that is. It might have been where the tubes and the exposure unit don't completely overlap, so it might have been that. Right, so I shall just rinse this in this, just to give it that last wee bit. Then I'm going to wash it to stop the development, and then we're going to etch this with ferric chloride. And now comes the etching, and I'm going to use ferric chloride. There are other etchants you can use. I've tried others. Some are really slow, some are faster. I'm going to dip this in, and when I dip it in, you'll immediately see that wherever the ferric chloride makes contact with the circuit board material, it immediately tarnishes. That lets you see if you've missed any bits on the, if you've left any of the etch resist on. Because even if it's an invisibly thin layer, it will stop the ferric chloride from making contact. And as I tilt this backwards and forwards, well, a good example might be, I don't know if you're going to see this, if I tilt this like this, you might see in the top corner, I'm not too bothered about it, I didn't clear off all the resist there, and it's just left a slight mottle, but it doesn't really matter, that's out with the cropping area. So I'm going to keep tilting this backwards and forwards. Now the ferric chloride, it is just it's a messy etchant, it stains everything, and you have to keep moving it, and it's also better heated. Now I just put the lid in this, and I put the lid on and closed down the end flaps but left the side ones open, and I microwaved it for just half a minute to heat this up. Not necessarily recommended because the corrosive vapours that come off it, if it sort of starts evaporating, will completely mess up your microwave inside the oven. But when you're a bachelor, things like that are perfectly acceptable. So what I'm going to do now is I'm going to keep rocking this back and forwards. Now, if you watch the channel Nerd Rage, greetings fellow nerds, he has featured various other copper etchants, and one of them in particular is very appealing because it uses an acid and it self-regenerates. If you just leave it in a container that vented to the ambient atmosphere, the oxygen in the air will recycle it and it continually replenishes, which sounds great, but here on an island it's so hard getting all these chemicals, particularly acids, because it has to be delivered to the island by hazardous shipments. What is the name of that? Hazardous shipping, I guess, really. So I'm going to pause now because this does take a while. And what actually happens is that it looks like virtually nothing's happening for ages, and you're tilting it backwards and forwards, it's washing backwards and forwards. The fresher the ferric chloride, the faster it will be, but it seems to take ages. But what it's actually doing is it's gradually eating its way down through the copper from the top. And then suddenly it all just starts etching away at once because it's so thin that it etches, particularly around certain areas where the solder resist, the etch resist, should I say, is causing slight local turbulence, and it's just let it cut in a bit deeper at that point. So it doesn't sort of, when it gets to the end, it doesn't instantly just disappear. It forms sort of patterns. That may also be down to copper thickness during manufacture. So I'll be back in a moment because I'm going to let this etch. This is just a quick snapshot of it mid-etch, so you can see that as it's starting to etch, well, I'll put the light under it, that will also show, it shows that the pattern it comes off in it's not an even pattern, it just suddenly starts etching in parts but not in others. So I shall continue the etching and it will shortly be complete and we can go on to the next stage. So etching is now complete and it looks a pretty good etch. And what I'm going to do now is I'm going to drill it. Initially, I was thinking, well, usually I just remove the etch resist material, and to do that, I just flood it with acetone. And after a while, it all dissolves and it comes off. Or you can put it into the exposing material, the developer, a much more concentrated version, just leave it for a while to clear. But in this instance, for drilling it, it's going to be easier because it provides a much darker visual image. And to drill it, I'm going to use this little drill, which it's a Minicraft drill, which is ancient. I got this from RME, Radio Mechanical Electrical in Howard Street in Glasgow, and you'd have to be of a certain age to remember that shop. And it basically takes a fairly standard, it came, I think, with various collets, but the best one is the one that takes these. Now, these are reground tungsten carbide bits. And the reason I call them reground is, I think these ones came from Rapid Electronics in the UK. You can also get them on eBay. These are used in the automated drilling machines, but they have to be the original length for those machines. Once they wear down, they can't use them because the machine would need recalibrated to the length of the drill. So what they do is, once they've used them to a certain degree, they send them away, and there are companies that regrind the tips, and then you can reuse them. And that's perfect for people like us who aren't too critical about the drill length. And also, they're so much cheaper than the brand new bits that it's just the only real option, because these are super fragile. Tungsten carbide will snap if you look at it. So it involves real control when you're drilling. So here's how I normally do it. Just to get the feel of the board, I will drill some holes out with an area that, the pads are. And in this case, I've left the pads with a tiny little indent in the middle, and that helps line up the drill. So I'm not going to torture you by making you listen to all the holes being drilled, but I'll drill a few of them just so you can see the process. So here's the test holes, and when you put it onto a pad like this one, it will kind of center itself. I'm using 1mm holes here because the LEDs are sitting hard down onto the circuit board. It's not necessarily a recommended way to mount LEDs, but in this case it aligns them up well, and by using a 1mm hole, it means that the slight meniscus of the resin of the LED will sit into that 1mm hole. I'm not going to torture you, as I say, with the drilling noise. I'm just going to start drilling my way along this, but you get the drift of what's happening. And every single hole in this board is actually just going to be 1mm, because the diodes are 1mm standard, and the other components like resistors, 1mm is fine. Normally for resistors I'd go 0.8mm, but in this instance, because I'm using 1mm for the LEDs, I'm just going to stick with that. And it is just because if you look at the back of the LED, if you drill the holes too small, there is just that little sort of wick comes up from the resin onto the lead. And it just sometimes, it means when the LED sits down, it can wobble. It doesn't sit down absolutely flush to the board. When you drill the 1mm holes, it sits down solidly onto the board and just locks straight on for drilling, for soldering. So that's the best option. So I'm going to drill this and I'll be back in a moment. Okay, so now it's time to fit the LEDs. Now that has been drilled and I've cleaned all the resist off. Now the older circuit boards, the ones that came with the resist, you used to be able to just solder with the resist on, but it doesn't work with these ones. It's almost like a plasticky layer. It just kind of shifts about, but it doesn't clear off the pads, so you have to clean it off completely. And I used acetone to do that. So the LEDs I've decided to use, I don't know if this is going to work that well, but I've decided to use, notice a little rag of resin here, I've decided to use the colour changing LEDs, the RGB slow colour changing LEDs, because I've got a huge bag here. Yeah, I'm going to have to try it at some point. I know the diffused isn't the ideal one for this effect, because it really needs this sort of highly focused lens effect, but it will still produce an effect. So I'm going to start populating the circuit board with these LEDs in this jig, and then I'm going to drill them, and then solder them all. And I'm going to have to be really careful to get these LEDs the right way around, because having trimmed the leads, it's actually a wee bit hard to see which way around. If I put them in the wrong way around, the high voltage will possibly nuke them. It might not actually, because these have a reverse polarity diode, I think, in the chip, which helps. I'm going to do that right now. I'm going to put these in, which will take a modest length of time, and then I shall solder them, and then we'll see what the resultant effect looks like. And now it's time to solder them in. Initially I'm going to solder just one pin of each LED, and then once it's kind of locked in place by that one pin that's soldered, I can then flip the board over, take a look, make sure they're all square before I solder the other pin. That also has the extra advantage of not overheating LEDs because only one pin is being soldered at a time. So I shall work my way along these solder joints as described, and I won't run the camera for too long at this because watching me solder basically 128 solder joints is going to get boring quite quickly. So I shall pause right about now. So that's all the LEDs on and nice and square. And the last thing remaining now is this capacitor. Now, I wanted to use an X2 capacitor. I don't have many really high values in this, so I've had to rob this 560 nanofarad capacitor out of a sort of cheapo LED lamp kit from eBay. And I'm not even sure if that's going to be enough because the combined forward voltage of these colour changing LEDs is going to be higher than just a single colour of LED. Typically about 4 volts per LED, and when you multiply that by the 64 it all adds up to quite a voltage. So that's much less to drop across the main, so I'm not sure this capacitor on its own is even going to run the LEDs anywhere near the sort of 20 milliamp mark that I want. I may end up having to add another capacitor in parallel on the back of this to boost that. So let's solder some leads on, and before I put it in the unit itself, let's test this and see if it goes bang or not. With main circuitry and modifications, there is always that slight possibility that something's going to go horribly wrong. So here is my live connection, which at least goes through a capacitor to limit the bang, assuming it's a good capacitor. If it's a bad capacitor, it will contribute to the bang and blow every single LED up. Don't want that. We shall see what happens. I don't think capacitor will be bad. There is other circuitry to kind of absorb the oomph there if it did do something terrible. So let's plug this into the Cliff Quick test and run it and see what happens and get a current measurement of it. So here's the Cliff Quick test. I'm going to put neutral in there. I'm going to put live in there, 240 volts, and we'll see what happens. Well, that's quite a good start. That LED has not lit. That's a bit disappointing. Why did they all light up different colours initially? Okay, that LED may be in the wrong way round. I've got the advantage, I've got a discharge resistor here now, that's quite good. No, that LED looks like it's in the right way round. Is there a solder bridge across that LED? Let's use a pointy thing to just double check there isn't. Oh, there may actually be a wee solder bridge across that, which I may or may not have removed. Okay, let's give that another go. No. Okay, I shall check that out afterwards. So it's all lighting up and it's changing colour. You may not see the colour changing because it's just dazzling the camera. So let's get the current through these LEDs by measuring the voltage across one of these resistors that's in series with them. So I'm expecting it to be within this 20 volt range. So let's see, what's it going to be? I would expect, oh, let's just measure it. It's 4 volts, roughly. It's bouncing up and down with the LEDs. 4 volts, hold on, let's do the maths here. I equals V over R, 4 divided by 330 ohms equals, it's only 12 milliamps. I'm going to boost that up. Right, one moment, I'm just going to see if I can find a different capacitor. So I had to go and rob a capacitor out of another light. This one is a 1 microfarad capacitor to get a decent current out of this. As the LEDs change colour, their voltage changes. So to work out the current for a start, let's set this to 20 volts and let's put it across this 330 ohm resistor. It's showing about yo-yoing up and down. It really varies. It peaked about 4.7, so do we just say 4 since it's a sort of average? Let's say 4.2, it's yo-yoing up and down. So let's say 4.2 volts across a 330 ohm resistor. 4.2 divided by 330 ohms equals about 12 milliamps, but it does peak higher than that. That's with a 1 microfarad capacitor. That's quite significant. Let's see what the voltage being dropped across the LED array is. So I'll include these two resistors in this by measuring across here, and I've got the meter set to a 1000 volt range because this is quite a high voltage. It's about 268 volts across those LEDs, but it will yo-yo up and down. That's quite a high voltage. So that's 12.7 times 268 equals about 3.5 watts for the light. Okay, that's quite interesting. I wonder if it's going to be bright enough. The only way we're going to find that out is to put that into the case right now. So I'm just going to unplug this. Let's put the calculator out the way. Let's bring the case up. I'll pop another capacitor into this. It seems a shame to deactivate it. It's the lamp with the microphone in it and the little dusk sensor. It worked quite well, actually. It was surprisingly good. But I'm not really keen on lamps that you have to clap to make them light. So let's bring the unit up. This is also where it would have been quite useful to have a little connector on the circuit board. Maybe I'll include that too. But then again, keep in mind that it's only me that's kind of swapping the circuit board out in this. And it is just two solder connections, so it's not exactly that complicated. Oh, you know what? Hopefully this will fit in. I did adjust the size of the circuit board a little bit. So that can go over there. This bit can go back in here. Here's the original circuit board. Let's hike this out. The power is off to this at the moment. And we'll desolder the connections off that. Oh, this one does actually not have a discharge resistor. I should actually discharge that electrolytic before I do this, but I'll get it later. With my finger, probably. Okay, so that's that off. Let's just check that, in fact. Let's short the electrolytic out. There's a wee spark, nothing really major though. Right, just out of interest, is this going to fit in? Yes, it is. That's absolutely fine. That's perfect. Okay, so let's get these original connections off and get the unit's connections on. So live is going through the capacitor to provide at least some limiting in the event of a terrible incident. And the neutral is going to the end of the bridge rectifier. Things worthy of note. The bridge rectifier in this, I staggered the diodes just because it gives much better separation. You can see they're sort of staggered here. That is it. So I'm going to put this into its typical focus position that the other one was fairly good at. I'm going to push it down hard. I can't resist it. I'm going to plug it in now. And see if it projects much light. I'm not expecting a huge amount of light out because it is diffused LEDs. Right, okay, it is projecting onto the wall. That is not bright. I'm going to have to take exposure off. It's kind of projecting. That is really dull. But I'm going to box this back up. I'm going to try it out and then I'll show you what it looks like. So here's the effect projecting up onto the ceiling. It's the attic room again with the angled ceiling. There's a light fitting up there and there's a pattern of dots down the wall. The camera is doing it a favour here. It's not as bright as it looks in the camera. But having said that, it's still visually quite good. I think if this was mounted close to a wall, maybe so the array of LEDs was just like 3 feet or a metre sort of square, it would have useful brightness in a sort of darkish room. It would have the effect of projecting those beams of light. On the other hand, I suppose you could actually just write a bit of software and have a LED projector doing this. But this has the advantage of the really random nature of the LEDs themselves and the power consumption. It's got no fans running. And the power consumption is something like, less than 4 watts probably. And it's just visually quite attractive, actually. It's very relaxed because each LED is just doing its own thing, so it just gradually morphs. So it's not that bad. Yeah, I could get used to this. It actually is quite a good result. It certainly had to be done to try it out to see how the diffused LEDs would work. And the answer is not as bright, but still a modest visual effect in the right environment. And this is it projected at fairly close range onto a door. So the display is actually just over 2 feet wide, which is probably about 600 millimeters square. So in the sense of projecting a sort of decorative morphing image, it's probably not that bad. It does provide decent intensity for that. The camera is doing it favours again here, but it's still, looking at it visually, it makes for quite a relaxing sort of pattern. But would I build another one? Probably not. I think I'd go for the focused LEDs again, just in interesting patterns as opposed to this one. But the thing is, it had to be tried to actually see what the effect was like, and I'll certainly be keeping this panel because it is a valid effect in its own right.